problem 13 of INYPT 2025, the spaghetti accelerator. Let's have a look at the problem definition. 1 second. Okay, there we go. Let's have a look at the problem definition. It says that when a piece of spaghetti is pushed into a bent tube, uh, when a piece of spaghetti is pushed into a bent tube, a small debris of the spaghetti may be ejected from the other end of the tube at a surprisingly high speed. And we are tasked to investigate this phenomenon. Here's the outline of my presentation. Firstly, I will be doing a qualitative analysis of the phenomenon, where we will discuss the spaghetti fracture dynamics in first an open area and then in a confined tube. Then I will be doing a quantitative analysis of the phenomenon. And finally, we will be closing it with my experimentation and the results that I obtained. Now, why does this phenomenon happen? To explain this, we first need to understand the dynamics of breaking spaghetti, which is an extremely interesting failure phenomenon studied by the likes of Richard Feynman that explains why spaghetti can only break into 3 or more pieces and never 2. So let's have a look at this paper from Arduli and Basile from 2005. The picture shows a slow motion capture of a spaghetti being bent past its limit curvature. Now, just very quickly to define what limit curvature is, when a beam is bent into an arc, every single point has a certain amount of bending in it that is defined as its curvature. The limit curvature is the max that that point in the beam can bend without it breaking. Now, in an idealistic rod, the limit curvature in all the points of the beam would be the same. However, this will not be true for a spaghetti, and the implications of this will be discussed later on. Now, let's have a look what happens as the spaghetti is bent. As the spaghetti is bent, the curvature of every single point increases until eventually one of the points suddenly goes past the limit curvature and it ends up snapping. Now, as this piece of spaghetti snaps, it sends flexural waves down the rod from the point of breaking. What these flexural waves actually do is that they go down the rod and they increase the curvature locally at a different point, causing a second fracture. Then the second fracture can send down more flexural waves, which can increase its curvature at a third point and cause a fracture there, and so on and so forth. This is why spaghetti will only break into 3 or more pieces and never 2. Now, this is an actual experiment. This is a qualitative experiment that I've done that explains this phenomenon. As you can see in this frame by frame capture of a video, as one point is about to cross the limit curvature of the spaghetti, the second it breaks, it causes multiple fracture points, and the spaghetti ends up breaking into 3 pieces rather than 2. Also, after it breaks, the spaghetti is oscillating back and forth, and this proves the flexural waves that I was talking about being propagated down the rod. Now, what happens if you confine the edges of the spaghetti as it's breaking instead of it being in a open area? Let's have a look. Right. So as we saw in the video, initially the spaghetti breaks at only one point. After the first break, the confined edges of the tube prevent the curvature of the spaghetti increasing at any other point, and therefore no other cracks form at either side of the initial fracture. Now, because of the extra energy that is gained by the release of the elastic energy, the unclamped piece, which is not being held down by my hand, flies out at a very high velocity from the other end, and that's exactly why this phenomenon happens. That's why the spaghetti accelerator works. Now that we're done with the qualitative analysis of this, let's move on to the quantitative analysis and form a theoretical model to see how the angle of bending of the tube affects the exit velocity of the piece of spaghetti. Here, let's look at the small arc in the spaghetti inside the tube where the bending is actually taking place. Let's consider a small fiber highlighted in red over here at a distance x from the central axis. The strain in that small fiber will just then be the change in the length of the fiber due to bending over the original length. The original length will obviously just be the same as the length of the central axis. So the length of the central axis can be found by the radius of curvature multiplied by the angle of bending, which is let's take as d alpha, a very small angle alpha, and we obviously take this angle in radians. Then we can use the arc length formulas to get that the change in length of the fiber will just be the new length, which is r plus x d alpha, or the new arc length minus the old length, which is just r d alpha, over the over the old length r d alpha. And therefore, we get that the strain in the small fiber at a distance x from the central axis will just be x over r, where r is the radius of curvature. Now, to find the stress in that fiber, where let's say y is the Young's modulus, obviously stress is just equal to y times strain. So we get stress is equal to yx by r. Now, if we want the bending energy per unit volume of each fiber, that will just be half times the stress times the strain. Hence, the total energy per unit volume of the fiber will be half times yx square by r square for every meter cube, because we're taking per unit volume, obviously. Now, if we sum this over the entire cross-sectional area of the bend, we will obviously integrate over the area A with respect to dA. And what we notice here is because originally we were taking per unit volume, and now we're multiplying that by an area that's meter square by meter cube. So that cancels out, and we're just left with one dimension of length. And if we look at the integral here, the integral of x squared dA fiber will just be half yeah, the elastic energy in the rod will just be half yi by r square. So then to find the total elastic energy over the full bend, what you will do is you will take just ds or rd alpha as we've shown here. Half y yi by r square ds. Now, if you want to model the exit velocity of the spaghetti, we know that the exit energy of the piece of debris that flies out. Let's take that. Kinetic energy is obviously just half mv square, and for elastic energy, we've just derived the formula as half yi by r square times ds. Equation where our exit velocity for the piece of debris is the square root of the input velocity plus yi by this phenomenon. There is some limitations, that those being that the mass of the debris must be measured after the experiment is over. However, as we will see later, the size of the spaghetti piece remains somewhat constant throughout trials. And hence, once the average is taken by measuring a few trials, it can be used to predict the velocity for all future experiments. Now let's look at the apparatus for experimentation. Essentially, what I did was I 3D printed multiple tubes with different bending angles, and I aligned them perfectly upright by taping them to a wall and using a level. And then I pushed a spaghetti through them using a syringe. Now the spaghetti was put inside the syringe and then pushed into the tube using the syringe itself. And hence, if the syringe is emptied across the same amount of time when pushing the spaghetti through the tube, which I did as 2 seconds, then we can say that the input velocity would have remained more or less constant, and hence same could be said for force. Now this then I took a slow motion video of the spaghetti exiting the tube, and using a software called Tracker, we can just do an analysis to get the exit velocity of the spaghetti. And these were the results. So, for example, for a bending angle of 10 degrees, the average distance the spaghetti traveled was 8.7 centimeters, giving us this experimental velocity. And we can compare that with the theoretical velocity 1.56 to see they're very, very close. Now, the theoretical velocity also has some margin of error, that being 7.4%. That is because the theoretical velocity also needed the use of the Young's modulus, which had to be measured experimentally. And it was measured experimentally for a few strands of spaghetti from the pack before the experiment, and the average was taken, ignoring all the outliers. So here is the final results that we get. As we can see, all the green data points show our experimental velocity for each bending angle, whereas the orange shows the theoretical velocity that we should have gotten. And as we can see over here, for about a bending angle of 25 degrees until there, our experimental and our theoretical velocities do match up very, very closely. However, past 25 degrees, we see that they have a big variation. Now, why is this? Well, if you experimentally measure the limit curvature of the spaghetti, you get it to be about 25 degrees. Hence, inside the tube, when theta is greater than 25 degrees, the spaghetti cannot fully go through the bend, and hence the piece of broken spaghetti, once it eventually ends up breaking, is still stuck inside the tube and it doesn't actually shoot out. And it only shoots out when the next piece breaks and comes and pushes it out, and then the next piece gets stuck. So from that, we can conclude that for all angles of bending less than 25 degrees, we know that the velocity of exit will be equal to the square root of the input velocity squared plus yi by mr square, the original equation we had seen. And for angles of bending greater than 25 degrees, we cannot accurately predict the exit velocity of the spaghetti, as the ejection of the spaghetti is pretty random, and it cannot be said whether the spaghetti will launch after every break. Now, another thing we notice when we're doing this experiment is that there is a relation between the angle of bending of the tube and the size of the piece of the spaghetti that is ejected. Here is the graph for all the bending angles of the sizes of the pieces of spaghetti across the trials. So as we can see, when the bending angle of the tube is much, much lesser than the limit curvature, the length of the ejected piece is varied over a very, very large range. However, when the bending angle of the tube is very close to the limit curvature of the spaghetti, the length of the ejected piece is very consistent, and it's around 0.66 centimeters. When piece is slightly smaller than limit curvature due to a more rapid bending, but even then, it's about consistent at 0.54 centimeters. Now, why does this happen? Why this happens is, since the bend is lower than the limit curvature, for about 10 and 15 degrees, for example, there is not enough strain on the spaghetti to cause it to break. Hence, initially, it just fully goes through the bend without breaking. But as I mentioned earlier, a spaghetti is not an ideal rod and it does not have the perfectly same flexibility at every point. The limit curvature varies across the spaghetti for every point due to irregularities in manufacturing and whatever. Hence, there are some points that are more rigid than others, where even the lower bend of the tube can cause it to break. Therefore, the spaghetti only travels through the tube until it reaches a point with higher rigidity, which then has a lower limit curvature, and it can break at the same angle, at the smaller angle. Hence, the spaghetti often travels longer through the tube for angles lower than the limit curvature, leading to the larger debris size. And that is everything that I covered in my report. Thank you, and that will be the end of my report.
Okay, Anahat, you have 50
Thank you,
seconds
sir.
more. 50 seconds more if you want to comment on some of the.
No, sir, I think I'll end it there. I have covered everything I wanted to.
All right, thank you, Anahar.
Yeah.
How did you ensure that the pushing velocity was truly constant throughout each trial?
All right. So, like I mentioned, I put the spaghetti through a syringe and I used the syringe in a constant amount of time. The input velocity should remain more or less constant.
All right. Did you control or measure environmental factors like humidity and temperature, which can affect spaghetti's mechanical properties?
No, but all the experiments were done right after opening the packet, so that should not have caused a very big difference in the mechanical properties of the spaghetti.
All right. What method did you use to measure the mass and size of the ejected spaghetti debris, and how consistent were these with these measurements?
So the method I used, as in I just use a vernier caliper for this length and a weighing balance for the mass. As for the consistency, I have shown the graphs. If you would like me to show them once again, I could.
No, I'm fine. Thank you so much. Sir, I think I'm done with my clarifying questions as for now. Do I have some time left?
Oh, I'm muted. Wait, once again,
Yeah.
let me verify that for each stage, each part, the allotted time is there. The person has to utilize the full time allotted.
Okay.
If you use less than the allotted time, you will be penalized. So, for instance,
Okay.
in this round, we had 30 seconds left, but now anyway it's gone, so it's okay.
Okay.
I'll just reset. So
Ganesh.
now you have 3 minutes to prepare. Now you have 3 minutes to prepare.
Okay.
Do you
Okay.
need
So,
3 minutes?
can I say no to this? Is it okay?
I think it is
Yeah,
okay,
you can
right?
say.
Okay.
Yeah, you can say for 30 seconds.
Um. All right. So I have 30 seconds to ask any clarifying questions that I want to Anahat.
Yes. Because that was
Okay.
left. Yes.
Okay. Okay. Um. All right. So the moment of inertia two is I think my voice is echoing, sir. Can that issue be
Yeah,
fixed?
it's all right. Sorry.
All right.
It
Yeah.
was muted.
Um. Okay. My question to the reporter is: the moment of inertia two is calculated assuming perfect cylindrical geometry. How did you account for the irregularities or the
Um, I
ovalization?
would I'd just like to clarify. I'm using the second bending moment of area as I stated. That's different from the moment of inertia.
All right. I'm asking, how did you account for irregularities or ovalization in the real spaghetti strands?
Yeah, so even with bending, the second bending moment of area should not change because the cross section will remain the same. It's just that the length of it's like there'll be more number of cross sections in the bending, but the each individual cross section should remain the same, right? So the second bending moment of area IY will remain the same along the neutral axis. So that should not the bending should not change it.
All right. Thank you so much. Sir,
Uh,
have I exhausted my 30 seconds in clarifying questions?
Yes, you have. You may begin with the presentation, right?
Yes.
Okay.
Okay. I'm assuming that my screen is visible. You can see it.
Yes, it is.
Okay. So I'll be starting in 3, 2, and 1. Hello everyone. Today I'll be opposing Anahat Johari on his problem spaghetti accelerator. Let's take a look at the problem statement once. When a piece of spaghetti is pushed into a bent tube, small debris of spaghetti may be ejected from the other end of the tube at a surprisingly high speed. Our task is to investigate this phenomena. We'll be looking at the strengths, weaknesses, the major scientific and logical flaws, followed by the recommendations for improvement. There are a lot of strengths in the reporter's work. There is a clear problem definition and motivation. There is use of established literature which references to well-known work by Adorley and Newkirk. There is a very sound attempt at quantitative modeling as well. The use of syringe for controlled high pushing velocity and slow motion video for velocity measurement shows a very experimentally thoughtful design. The presentation admits that for bending angles above 25 degrees, the model breaks down due to jamming and stochastic ejection, indicating some awareness of model boundaries as well. The reported 7.4% average error between theoretical and experimental exit velocities suggests the model captures some key aspects correctly as well. Let's take a look at the 5 key scientific and logical flaws in the reporter's work. Firstly, the whole model has been very oversimplified. The tube confinement is claimed to stop further cracks without addressing fracture cascades or wave propagation as well. It assumes full elastic bending energy, which becomes kinetic, ignoring heat, sound, damping, and wall friction, overestimating the exit velocity as well. Secondly, the spaghetti model as linear elastic, ignoring viscoelasticity, brittleness, moisture, and manufacturing variability. Furthermore, the moment of inertia and mass is assumed constant, which ignores the shape irregularities as well as the fragment variation as well. Thirdly, the syringe mechanism ignores pressure, friction, and slipstick effects. The exit velocity has been derived using ideal projectile motion, neglecting air resistance, spin, and alignment errors as well. Furthermore, there is no control of humidity or temperature despite their major influence in this research. Fourthly, the 7.4 error cited without statistical backing misses sample sizes, confidence intervals, and error propagation as well. It claims about jamming and fragment size, but lacks quantification or microscopic validation in it as well. Lastly, the research ignores fracture toughness, strain rates, air drag, and aerodynamic effects. There is no exploitation of tube material, curvature, or high speed strain measurements as well. So we can say that it lacks control experiments for comparison as well. The research loses its validity when the reporter assumes coolly that all elastic bending energy converts into kinetic energy without losses, which is completely unrealistic, undermining the theoretical velocity predictions. The reporter ignores viscoelastic and fracture toughness. There is a complete lack of rigorous experimental controls, environmental, geometric, and measurement uncertainties, which weakens the reliability of the data. There is an absence of detailed statistical treatment, and error analysis limits confidence in conclusions. And lastly, the model fails to predict behavior beyond 25 degrees bending quantitatively, leaving a significant part of the phenomena unexplained as well. Um, as the opposition, I would recommend the reporter to measure Young's modulus, fracture toughness, and viscoelasticity under controlled environmental conditions. I would recommend him to use high-speed imaging and strain gauges to capture real-time fracture and validate strain assumptions. I would also recommend the reporter to quantify losses to heat, sound, friction, and deformation using calorimetry or acoustic tools as well. The reporter could replace basic SUVAT methods with label Doppler motion tracking for precise exit velocity. The reporter further could increase trials, report deviations in confidence intervals, and apply hypothesis testing as well. The reporter could investigate how tube geometry and material affect fragmentation and injection dynamics. The reporter could investigate and integrate dynamic fracture mechanics and viscoelastic behavior into their theoretical framework, and he could test with straight tubes and varied bend angles to understand the full response range as well. Concluding, the presentation is a commendable initial exploration of an intriguing physical phenomena with reasonable theoretical framing and some experimental effort. However, it suffers from oversimplified assumptions, incomplete experimental rigor, and insufficient data analysis. Thank you. Um,
Now you can call the
Thank you,
reporter
Sukada.
for discussion.
okay.
Yeah, for 10 minutes, you can have a discussion
Yeah.
with the reporter.
So to start the discussion, you mentioned a couple points in your opposition report that I just like to clarify.
Mhm.
Yeah. So if I let me just share my screen really quickly. Yeah. Okay. So the first thing you mentioned, I remember you mentioning, is that I should have not used Hubbard equations, which were not in my report, and I should have used a software analysis, which I have clearly mentioned I did. Um, Secondly, you said that I needed to use high-speed imaging to see the fracture dynamics of the spaghetti. I have used high-speed imaging over here when I see the velocity, when I see the debris shooting upwards, and to measure the velocity for that. Also, for the exact fracture dynamics and breaking the spaghetti, I have not used high-speed imaging myself, but I have cited a source that did, and I was able to get the same result. I was able to get the result of analyzing the high-speed imaging. Um, Also, you mentioned that the 7.4% error is between experimental and theoretical values. You also mentioned that it's cited, which is just not true. That I clearly mentioned I did the experiments myself. I did it. But anyways, you said that this 7.4% error is between the theoretical and experimental velocities. I just like to clarify that is not what it is. The 7.4% error is the error in the number given in the theoretical. So, for example, if I say for a 10-degree bending angle, my theoretical model predicts a 1.56 meters per second exit velocity. This error comes because I needed to use the Young's modulus for the theoretical model, and the Young's modulus had a 7.4% error when I measured it myself. That was the deviation. So that's where the error comes from.
All right. I'd like to ask you a few more
Right.
questions on your data analysis and interpretation.
Right.
Right. Did you mention the variability in debris size due to rigidity variations, but provide no quantitative data there? So,
Yeah,
did you
so
measure?
here is the quantitative data if you'd like to have a look.
All right. Um, okay. Could you clarify more on why the model fails beyond 25 degrees of bending angle? Can you explain the physical mechanism
Yeah,
behind the
Yeah,
failure?
so like I already did in my report, essentially what happens is that 25 degrees is the rough limit curvature for most of the points in the spaghetti. Now, like obviously, because it's not a perfect beam, as both of us had said in our individual reports, there will be some variation in the limit curvature, but 25 is what is true for most of the points of the spaghetti. Now, when the spaghetti is pushed through the bend, what happens is when the theta is greater than 25 degrees, the spaghetti can't actually move through the bend, right? When it's less than 25, the spaghetti can move through the bend and only fractures once a little bit of the spaghetti has already moved through the bended part and gone to the um gone to this second part of the tube. But when theta is greater than 25, since the spaghetti can't actually fully go through the bend, it breaks before it can ever reach the exit before it can ever reach the exit part of the tube. So it just collides against the wall and it stays right there inside the tube until the next piece pushes it out. That's why above 25 degrees, the exit velocity is considerably less than what you'd expect it to be, because the actual exit velocity is not being measured. What's being measured is when it gets pushed out due to the next piece.
All right. How do you justify treating spaghetti as a purely elastic material with a single Young's modulus? And in doing so, you ignore all viscoelastic or brittle fracture behavior as well. How would you
Uh,
justify that?
Yeah, so this is obviously just an approximation like every theoretical model out there. So as you can see in my experimentation, the limit curvature is more or less this same. The elasticity is more or less the same across most points of the spaghetti. There are some variations which I have analyzed later, and then obviously when those variations come into effect, there will be some variations from the model that I've given. But this is just an approximation for the best. This is the best possible thing you can do, and this is just an approximation. So that's the model I've gotten. If you want for a specific point, you can find the Young's modulus for that point and sub it into the model, and you will get your answer. But obviously, when dealing with any rod, you will be like approximating the Young's modulus for the full thing. You won't go into every individual point along the rod and measure the Young's modulus for that.
All right. Since we're on the slide where you talk about the 25-degree bending limit, what additional experiments or measurements would you propose to improve the model's predictive power beyond the 25-degree bending limit? I think this is a serious limit of validity in your overall
Um,
research.
yes.
What would you
So
suggest to?
don't see this as as it being less valid because of a limit in the model, because fundamentally you're only gonna bend the spaghetti until its limit curvature, right? Past the limit curvature, it makes no sense to, like, if the limit curvature is 25 degrees, you can't predict what will happen when the tube is 40 degrees because it'll break inside anyways. So if you want, you could kind of like do an analysis of how much the next piece will hit how much velocity the next piece will hit this piece with, but it's honestly very random and I don't think that can be properly modeled.
All right. Um, okay. So the reported 7.4% error is attributed mainly to Young's modulus measurement uncertainty. Now, how many samples did you test and what statistical methods did you use to estimate this error?
Yeah, so sorry. So I tested 5 samples, and essentially I just took the deviation from the mean.
Could you mention how many trials you took again?
5.
Okay, 5, right. Okay, have you considered measuring dynamic fracture parameters like crack propagation speed or fracture toughness to better understand the breaking process in the future?
Could you elaborate a little more on what you mean by that?
As in, have you considered measuring more parameters like crack propagation speed or fracture toughness in the future?
Okay, what do you mean by crack propagation speed exactly?
I mean, as in when your spaghetti is going to crack and the speed that is given out by your debris.
The
Maybe
speed that is
if
given
you
out, the
understood
speed that
it.
is given out is already modeled, right? That's the whole point of the report.
Right,
And as
right,
for
right.
when it's going to crack, it's going to crack once it goes through the bend. Now that's when it reaches limit curvature. I'm not sure exactly what you want me to model in that exactly.
Okay, I think I didn't frame the question properly.
Yeah.
I wanted to ask you if you are going to research further, considering all the energy losses, considering the humidity change as
Okay,
well
right.
as the temperature.
Yeah,
So,
so obviously, if you want to consider the energy losses in the fracture and all of that, you can do a lot more research there. But this is just an approximation for what we can get, and this is an idealistic model. It would be very difficult to see the exact energy loss, but obviously there is always more scope for research in every field. You
right, right. Did you perform control experiments with a straight tube or different tube materials to isolate the effect of
I'm
bending
sorry,
radius?
if it's a straight tube, how will the spaghetti break?
Right. Okay. Have you considered doing it with different tube materials? Is it going to impact
Um,
your research in any way?
So I have not done any experiment for that, obviously. But honestly, I don't see how the tube material could affect the bending of the spaghetti, because at the end of the day, the spaghetti just has to go through the hole, right? So whether it's a metal tube or a plastic tube, the spaghetti is bending the same.
No, it actually could. What if your tube is made out of rubber? Then I think it's going to
Then
impact it.
if the tube isn't rigid, then probably it'll just be a lot harder to break the spaghetti, right? But it's
Exactly.
that's Yeah, so that has not been experimentally measured, but that's a whole other statement itself. The problem statement is about the exit velocity of the spaghetti.
Right. Could I please know how much time I have remaining?
You have 1 minute 30 seconds, 35 seconds.
All right. Let me just think of a few more things that I can ask the
Okay.
reporter here.
Yeah. So since you mentioned a lot about energy losses, how would you suggest that I try to model the energy losses in this scenario? Because honestly, the energy loss due to sound or heat will be frankly very minimal, and do believe most of the energy is going to go to the exit velocity anyways.
It is, it is. Um,
Well, if it is, then why would you think I need to model it? This
I'm
is
sorry, as in?
if you do agree that most of the energy is going towards the exit velocity and very minimal energy is being lost, then why would you want to introduce that complexity into the model for no reason, since you keep mentioning it?
Well, I don't see it as introducing complexity into the model. I see of it as trying to reach, as trying to become more experimentally sound. Because, I mean, the whole
But
purpose of this
yeah,
is
yeah. No,
to.
no, I get your point. But if this model is going to give you a pretty good approximation of what you get experimentally anyway, what would be the point of adding that entire energy loss dynamic?
I don't disagree with the fact that your research currently is not giving a very good experimental modeling. Of course, it is. But I think you could improve the scope of the research if you try to inculcate all of the energy losses as well. I'm not asking that you should right now at this moment,
Okay,
but if you look at it as a
perhaps, yeah,
problem
yeah,
statement, yeah,
perhaps that could be done. Sure.
yeah, like maybe not at the high school level,
Right,
but
right, right.
for the
Okay.
whole, yeah. I hope you got that. All right. What are some real life applications of this phenomena?
Uh, I,
Are there
yeah,
any?
I think Sir is trying to say something.
Okay.
Your time is up.
Okay. Okay.
So now is the time for your summary. Any 1 minute summary you have about your discussion.
Okay, your time starts now. I keep forgetting that I'm muted. Sorry. Are you able to hear me?
Yes.
Yes.
Yes, Sugata, you have 1 minute to summarize the discussion which you had with the reporter so far. 14 minutes. Can we start the timer?
Can I have like 20 seconds or something to just
Yeah.
No.
point? Okay,
Why?
no? Okay.
No.
Sorry. All right. So starting in 3, 2, 1. So I have to summarize everything that started with the report, the opposition, and the discussion that followed, right?
Yes, you have 1 minute.
Okay. Yeah. So starting in 3, 2, 1, the reporter started with. I'm sorry. Yeah. So the reporter started with clearly laying out the problem statement, and furthermore, the reporter talked about. Okay, I'm sorry. Uh, can I start again? I'm so sorry. I froze.
Just proceed.
So sorry. I'm so
Okay.
sorry. Yes.
It's
Okay.
Yeah. I just forgot to get the tab
Okay,
that
you
it's
opened.
take
okay.
10
Just
seconds.
proceed. Just proceed.
No,
Yeah.
Akshat, don't hurry up the opponent. Later, take 10 seconds to collect your thoughts, and then we can start. Not a problem.
All right, it's all right.
Okay.
You
Yes.
take 10 seconds to collect your thoughts, and then you
Yes.
start. Tell
Sure.
me when you're ready. 10 seconds.
Yeah.
So I think your mic
Ready?
is echoing also. Can you mute?
Yeah, I mute myself.
Yeah.
I'll.
Okay.
Okay, timer starts.
Yes. The reporter started with stating the problem statement as well as lined out the reason for this phenomena and talked about why it is an extremely interesting failure phenomena. Furthermore, the reporter showed a slow motion capture of spaghetti being bent past its limit curvature and showed that the breaking limit at the angle is 25 degrees. The reporter clarifies that the spaghetti initially breaks at only one point, and after the first break, the confined edges of the tube prevent the curvature of the spaghetti, increasing not at any other point. Furthermore, the reporter also quantitatively analyzed the whole research, showing the strain of the small fiber from the center axis. The reporter then showed his apparatus for measuring the exit velocity and pointed out the errors that is 7.4% in his Young's modulus theoretically, that is 7.4%. Um, the reporter furthermore showed that the spaghetti breaking debris failed till it reaches this tilting point with higher rigidity, which has a lower limit curvature and can break at the smaller angle. Now, the opposition pointed out the flaws in the opposition. Is my time over?
Yeah.
Oh, okay.
Okay. Thank you.
Now,
Okay.
reviewer questions the reporter and the opponent. So
Okay.
you asked for
Okay.
5 minutes time, right?
Yes.
You
Sir,
wanted
Adishwar is
5 minutes?
there. Adishwar is the reviewer, right?
Also is there?
Yeah,
Yes.
I'm here.
Oh,
Sorry, I joined a
Also,
couple of minutes
why
late.
were you late?
Yes, I'm really sorry. I was actually stuck in Bangalore traffic, and I predicted when I'll reach home pretty wrong. But I was able to listen to Sukhada's opposition as well as some parts of the report, and I went through the report itself too, and I got the questioning too. So I believe I'll be able to give a good review.
Okay. So then you let me see what stage you are. You have 3 minutes to question. Do you want some time to prepare or you're ready?
Yeah, I'm ready.
Okay, tell me and to start the timer. 3, 2, 1, like that.
All right. Yeah, I'll just start the time on my first word. So I'll
Yeah.
basically first ask questions to Anahat, a couple of questions that I had while I was reading his report, and then I'll move on to Sukda. So my first question to Anahat is basically about the model itself. So why did you like choose to assume that? Why did you choose to assume full conversion of elastic bending energy to kinetic energy despite energy losses as Sukta mentioned? And even if it's like out of the scope for this research, uh, what do you think the realistic
Yeah.
margin of error would be, like
Yeah.
ignoring sound
So,
heat and all?
yeah. So, like I said, realistically, the amount of energy loss is very, very small because you're not creating that much friction or sound inside the tube. And this can be like verified by seeing the experimental data, and it is matching up very, very closely to the model. So I feel that the model still holds true even though it doesn't account for any energy losses, mostly because even though it's definitely not 100% of the energy being converted, it is still a very large percentage that is going to the exit velocity and very minimal loss in comparison.
Yeah, that's completely valid. I would just say it's kind of helpful to sometimes quantify your margin of error. Like what I'm getting right now is that the margin of error is obviously pretty low. But yeah, it helps to quantify it sometimes. But yeah, that was like my first question to Anahat. My first question to Sukhda would be I believe you criticized the use of a linear elastic model and like the neglect of, I think you mentioned viscoelasticity. Is that right?
Yes, I did.
Okay, so if that's not what Anahat should use, what do you think some other models he should use? Like, what specific alternate models do you think would be good, or like other corrections?
I'd like to clarify that when I was talking about viscoelasticity, I was referring to Anahat's complete ignorance of talking about the humidity as well as the material defects of the spaghetti itself. I was not talking about the tube that he used. So I believe that rules out the necessity for having a new model completely.
All right, so the correction you'd recommend is not neglecting viscoelasticity itself. All right, yeah,
Yes.
that makes sense. Okay, wait, I have one more question to Anahat. I believe I have like 1 or 1.5 minutes left.
Yes, you do.
All right,
Proceed.
yeah. Okay, yeah. So my second question would be, uh, okay, wait, actually, your model breaks down beyond 25 degrees, as you said. So did you like try fitting or extending the model to those ranges and fail, or did you like assume it would, or did you like deliberately exclude
Yeah,
that?
yeah, yeah. I deliberately excluded that, and I already mentioned why in the discussion. The spaghetti will never bend past 25 degrees, even if the tube has a bigger bending angle. So realistically, what just happens is that once the spaghetti is done bending to 25 degrees, it breaks and the debris gets stuck inside the tube. So then, modeling how it'll exit by the next piece of spaghetti coming and pushing it, that's just a very random behavior, and that can't really be modeled, according to me. So I deliberately excluded that. I
All
had
right,
mentioned this
yeah.
in the discussion as well, I think. Yeah.
Okay, yeah, that makes sense. I believe, wait, you mentioned your sample size was 5. I think you reported like a 7.4% error.
Yeah, just yeah, in the Young's
Also,
modulus,
time is
yes.
up.
Okay.
Time is up for this part.
Okay,
The next part is
Your
we
preparation,
have 2 minutes
preparation.
to prepare. 2 minutes to
all
prepare
right.
your
Yeah,
speech.
all right, yeah,
So
that
if
sounds
you
good.
cannot, okay. After the 2 minutes, you can prepare your review speech. You will have to
Yeah,
speak for 4 minutes.
all right.
No.
Okay, 2 minutes is over, right?
Yeah.
Okay, I'll just
Now,
set a timer for 4 minutes.
tell me when to start.
Yeah, sure. All right, I'll start the timer on my first word. So first what I'll do is I'll just recapitulate what the core scientific question was and then move on from there. So Anand's report aims to investigate kind of an underexplored question, which is can elastic energy from breaking spaghetti be harnessed to like propel its fragments in a predictable way? And I believe the novelty lies in treating spaghetti fracture not as an end itself, which was done in a couple of research papers in 2005 by, like, say, Audley, but as a launching mechanism, which is why it gets the accelerator sense. So yeah, so now moving on to Anahad's model. So his theoretical model, I'll just list what his theoretical model assumes first. First of all, it assumes like linear elastic behavior of spaghetti, which makes sense in most material science research. He also assumes full conversion of stored elastic bending energy to kinetic energy. This was also the subject of a dispute between Anahad and Sukha. Also, his model assumes idealized moment of inertia of the spaghetti and mass distributions. He also assumes neglect of fracture toughness, neglect of viscoelasticity and damping, and other loss factors. But yeah, in response to the critique, Anand defended the full energy conservation assumption by basically saying that the energy losses are too small to affect overall velocity significantly, and that is true in some contexts. No quantitative justification or sensitivity analysis is presented to support this claim. Like, at least a quantification of his error margin would be helpful. He also justifies using Young's modulus as a practical approximation, which is fair in initial modeling. But Sukada also rightly notes that spaghetti is viscoelastic, especially under dynamic fracture. So but yeah, her suggestion to include viscoelasticity itself lacks specific modeling advice. Like, when I asked her, she said how he neglected viscoelasticity and he should include viscoelasticity, but just saying that is not really specific enough. Moving on to the experimental methodology of Anath, he basically designed a syringe tube mechanism to break and confine spaghetti, with also velocity estimation based on projectile motion. He also claimed of using high-speed imagery to validate observations, supported in part by cited videos and one figure, but the raw data like sample size and imaging parameters are largely absent from the report. To critique this, Sukada accurately challenged the lack of statistical treatment in her opposition. She also noted the absence of controlled experiments like humidity, which of course Anahat also went on to defend in the question answer session. But Anahat also conceded that finer controls are possible, but he emphasized his model is the first approximation in a sense. I mean, it's a fair position, but it's still not sufficient enough to claim like general predictability, as claiming predictability is a pretty big thing and you need to be as precise as you can. The report also I believe the report also, Anand explicitly limited the scope of his model to bending angles below 25 degree. He cited that the behavior beyond this point becomes chaotic and random. This is pretty reasonable and a scientifically honest answer. But the trade-off is, of course, that the model only applies to a narrow and idealized subset of spaghetti fractures, and it can be debated whether the question wanted that or not. But yeah, that's a fair point from his side. So ultimately, like, both Anand and Sukda made reasonable and insightful points, but left some gaps. So yeah, that's basically 4 minutes, I believe.
Thank you, Adeshwar.
Now, reporter will have 2 minutes to give concluding remarks.
Reporter, you have 2 minutes to present concluding remarks.
Could I just get a second?
Yeah, tell me when to start the timer.
Is my screen visible, by the way?
Yeah.
Yes, Akshat.
Okay, let me start the timer. It's 2 minutes, right?
Akshat, are you sharing the stopwatch?
Yes, I am.
Actually, if you share the stopwatch, I can't see the student's presentation. So that's why I stopped sharing. So you also stop sharing. Anyway, the students are individually opening the stopwatch in their screen, and I am having a buzzer. So don't share your screen.
Okay, so you raise your
I'm
hand
not
once
able to
the
see.
time is up. Okay,
Yeah.
raise your
Okay.
hand once the time is up. Okay, all
Am
right.
I not audible? Am I not audible when I say time is up?
You are audible, but
It's
you know,
it's not
Okay, I
clear.
also raise my hand.
it's not
Okay.
eligible, kind of. That's why.
Okay. Now shall I start the timer?
Anahat, shall we begin?
Yeah, sure.
Okay. Yes, sir.
Okay.
Yeah, start.
So throughout the report, the reporter presented a theoretical model in his throughout the report. The reporter firstly presented a qualitative analysis of the phenomenon, then a theoretical model, which was then experimentally verified using his control setup, and was proven to work at at the limits that he stated. In the discussion, there was a couple disagreements that were brought up. The main disagreements were on the fact on the whether or not the model not going past 25 degrees is a limit for its validity. Here, I still strongly would like to present that I would still like to strongly state that a spaghetti is never going to bend past 25 degrees anyways. So a model only going up till that point should still be considered valid, because even if your bending tube is greater than 25 degrees, that's just not true for the spaghetti itself, and the problem statement is about the spaghetti. Uh, Furthermore, there was a couple more disagreements based on the energy loss. Here, I would there here, the main disagreement was that the reporters stated that the model was sufficient even without any modeling of the energy loss, whereas whereas the opponent as well as the reviewer both would have wanted an incorporation of the energy loss in the theoretical model. Here, I can concede to the fact that perhaps a slight analysis of the energy loss in the model would have been slightly more appreciated. However, even an idealistic model such as the one presented is providing a very good approximation for the experimental results that we have gotten in the phenomenon, and hence can be considered to be very valid. Uh, the third disagreement was about the viscoelasticity of the spaghetti, where the reporter has already stated multiple times that whenever you're dealing with a rod, you will consider a similar elasticity for all points, even if that might not always be consistently true. And the points of the elasticity is different compared to others are very, very few points that are not actually going to come up. Uh, and hence it should be okay to consider the constant elasticity throughout the spaghetti. Those are the main disagreements in the report, in the discussion. Thank you.
Yeah. Now it's time for the jury to ask questions. Uh,
Let
we
me
will
begin.
take.
Can I begin?
Actually, I want to.
Yeah, Akshat, are you going first?
I would like to go first.
Okay, let
Okay.
let
Okay.
Mr. Gyani go first.
Okay, I'll start the timer. My question is for the reporter.
Yes,
I
sir.
feel that the limitation is not with the theoretical model, but with the experimental way of collecting your data. Suppose you did your data collection like this instead of what you did. Instead of manufacturing 3D printed bent tubes of predetermined angles, suppose you took a capillary tube with a single linear hole, and first you in your speech you even said that how can we bend the spaghetti if you pass it through a linear tube, right? Now just imagine this situation. You take the capillary tube at a different angles from the
Sorry,
horizontal
I think,
surface.
sir, I'm really sorry. I think if you're trying to show something, then I can't see it. If you're just explaining, then
No, I'm
because you
just
keep it.
explaining. I'm not
Okay,
saying.
okay. Sorry. You said like this, so I thought maybe you're showing something.
Just imagine that you are tilting the capillary tube at different angles from the horizontal table surface. The table surface is rigid. So, and you push the spaghetti through the capillary tube, and the diameter of the capillary hole is exactly equal to the capillary spaghetti. So, it acts like the bent tube only. So now when the spaghetti is getting bent by pressing against the table surface, it will break eventually. So you can change the bending angle by changing the angle of at which the capillary tube is with the table. So now I think even if you increase the angle beyond 20 degrees, like 40 degrees, it will still break. It will continue to break. The length of the broken pieces which fly off will vary. They will get progressively smaller and smaller as the angle of the capillary tube with the table increases. Now, what do you have to say about this suggestion?
Um, Yeah, so this is definitely a good suggestion. It can be explored, but what I would like to say is that even if you keep the capillary tube at an angle that is bigger than than the limit curvature, the sa the that's isn't that the same as what I've done with a 3D printed tube that has an angle bigger than the limit curvature? A spaghetti has to go through a bend that's greater than 25 degrees, and therefore it'll bend very rapidly, and it'll break off before it actually ends up going through the bend completely, right? So wouldn't that provide the same results?
No, it won't provide the same results. The key difference is in your vent tube, you have an outside, you have a part of the tube after the bend. So it gets stuck. The broken piece gets stuck in
Oh,
that part.
sorry. You mean push the
When it
spaghetti
gets
through the tube
stubborn,
and onto the table?
yeah.
Oh, sorry. I was thinking of it the other way around, from the table
So
to the
now
tube. Oh, okay.
the,
Yes.
the
Okay. Yeah.
part
Then
after the bend is missing. The
yeah. Yes.
tube doesn't have a part after the bend. So it just pushes on the table surface, bends, and
Okay.
breaks
Yeah. I
and
see.
flies off.
Okay, yeah. So, so for as for the size of the spaghetti, that is definitely one more way that that could explore it, and maybe perhaps that would be have been a slightly better setup. But the way what I would say is that if you use that setup, when your spaghetti breaks off, it's gonna hit against the table and everything a lot. So you can't measure the exit velocity accurately, anyways. And as for the size of the spaghetti that's coming out, that I have already analyzed using the 3D printed tubes itself. If I could share my presentation. Um, right here, I've analyzed the size of the spaghetti as the bending angle increases past limit curvature with the use of the tubes. So I think I have been able to do the same thing even with my setup and accomplish the same result.
Over to the other judges, question to the opponent and reviewer.
I think Shardul has some. So
Oh, yeah.
Yeah.
Okay, so okay. So I want to ask Anand
Right.
about
No,
instead,
Anand
like,
has already been asked one question. We have to cover all three, opponent and reviewer also. Can you ask a question to the opponent?
so I don't have a question for the opponent. I have
can
a
I
question
ask
for
a question
Anand.
to
Yeah,
opponent?
yeah.
Yeah.
Go on.
Yeah.
Sukata, can you go to slide 10 and slide 10, first point?
Slide 10 of my opposition. Okay.
Yes.
Right. Just a minute. Um, right. There it is. Saying slide number 10. Okay. There.
Okay, what do you mean by replacing basic SUVET methods with laser Doppler or 3D motion sensing and something like that? First of all, what do you mean by basic SUVET methods? And second point, why do you think it can be replaced?
Um, so it basically represents distance u for initial velocity, v for the velocity at the time, and a as the
Okay, yeah, I
acceleration.
get it. What do you
So
mean by
that's where.
replacing it?
I think that the basic modeling that has been done for velocity is crude, and it could have been improved if we talked about all of the SUVET.
No, it's still not clear. Can you be more precise in what do you mean by replacing those SUVET methods? Because it is basically an expression for acceleration with velocities and displacements, right?
Yes.
How can you think of replacing it
Yes.
with laser Doppler or 3D motion tracing or something like that? Like they are completely irrelevant, right?
Could you clarify a bit on that?
How do you think these methods can replace the latter three things you have described in the first point? How can they be
When
replaced in
I
the
talk
first
about
place?
laser Doppler,
Oh,
Yes, laser Doppler or 3D
uh,
motion tracking. Yes.
Akshat,
when I
the
talk
thing
about
is,
LDV,
she was confused because see, Anahat did not use SUVAT methods to find the exit velocity, right?
Mm-hmm.
Here, what she's doing. She's about velocity accuracy. She's trying to find the. She's saying that Anahat used SUVAT method to find the exit velocity, which he did not. So she's saying that he should instead of SUVAT methods use tracker or laser Doppler method
Uh,
to find the exit velocity, to measure the exit velocity.
So Sukhada, are you essentially saying the linear acceleration assumption was discouraged here? Is that what you meant by SUVAT?
Roughly, yes. Yes.
if I
Yes,
may.
Anahat? Yes.
Yeah, so I think, but then for the finals, I have used tracker and used a software analysis and replaced the data with a fresh one. So I think she probably put this in with my first round's presentation and didn't remove it when I present it right now.
Do you
I
Yes.
agree
think
with the
that's what
fact that linear acceleration is not the thing going on here?
me,
Yeah.
as in.
The linear acceleration, which can be modeled with these basic SUVAT equations.
So the way I had done it originally in the first round was that I had modeled the exit velocity by just seeing how far up, high up the scale this piece of spaghetti goes, and then just like let's say it travels 80 centimeters up into the air. So then I use SUVAT equations to calculate what the exit velocity must have been. But I realized that there is a lot of air resistance and other factors that would probably reduce the validity of that and would not give me
Okay,
an accurate
okay,
answer. So yeah, that's why I switched to tracker for the fresh data, and my
okay.
new
I get
data
it.
is all with tracker. Yeah.
I get it. Thank you. Thank you, Anahat. Thank you, Sukhada. Adishwar, what are your comments about it? Adishwar, what are
Is
your comments
Adishwar
about
here?
it?
My comments on this discussion or the entire like
This discussion
This
about
discussion.
SUVAT.
okay. Okay, yeah, I mean, on SWAT, I mean, first of all, it's obviously pretty accessible and I think it's easy to implement. Um, but one major con is it assumes like ideal projectile motion, which we know is not true, like assuming air resistance and even alignment errors. So obviously, like if you use something like laser Doppler, it's going to be more accurate, but it's also more complex and maybe not practical at this stage. I would say that in Anad's case, using SWAT is justifiable, even if he used it for the second part, not only the first, because his goal was to develop a first order approximation. So if he wants it to be a first order approximation because he neglects air resistance and energy losses, then what's the need for more precision when it comes to tracking stuff like speed and velocity, right? So, yeah. Um, maybe
Okay.
Okay, I have a question for the reviewer.
Thank you, Adishwar.
Reviewer, Adishwar. Adishwar, can you hear me?
yes.
Yeah, so my question for you is, do you think Anath could have overcome the limitation of the 25 degrees by using a capillary tube and pushing the spaghetti through it at different angles so that it hits the table surface and then breaks and flies off?
Oh, um, yeah, I mean, I guess he could have explored like the greater than 25-degree regime by using the capillary tube, because it would reduce like the randomness of the post 25-degree fragmentation that we discussed, and that was the major issue in exploring beyond 25-degree. But that would obviously also like introduce complications um like there would be wall friction and all, but then again, if it's a first order approximation, I guess wall friction and pressure gradients don't matter. So yeah, I would say it's valid to extend the study beyond 25-degree even at this stage, um because like he's expanding the regimes that he's counting from just how spaghetti breaks naturally to how it breaks under confinement, I guess. Yeah.
Okay.
So you think there is a scope for further analysis, right? Beyond this
Yeah.
critical angle. Okay.
So do you think
Yes.
that this critical angle, like, it can be increased to some extent,
Yes,
like
using
greater than 25 degrees?
I think the major issue with greater than 25-degree was randomness, and I believe Gyaneshwaran's sir recommended the capillary tube approach to reduce that randomness. So I guess it can be extended beyond
Right, that is
25
also a point because I've seen that there's a misunderstanding between limit the curvature and angle, because angle is not curvature throughout. Okay,
Yeah.
in his model, he hasn't taken curvature into account technically. because the 3D model which he printed was a direct angle change, right? The whole of the his spaghetti was not curved. Curvature is 1 by radius. So if you put it into Sir's model, then if you like bend the whole uh, capillary tube in about like a certain radius, then you could have talked about this limiting curvature, and then maybe you could have gotten like a higher angle or like a higher limiting radius. So we could have done more experiments about that. Yes, Anahat, you want to say something?
Yeah, just a few things. For one, for the thing between confusing angles and curvature, I agree that those are two separate concepts. But basically, what I'm trying to do here is, I used curvature in the model. I used the radius of curvature, which is just one by curvature, and
Which is
as
1 by
for and
radius. Which is 1 by radius.
sorry,
Curvature is 1 by radius.
yeah, therefore radius is one by curvature, right?
Yeah.
Yeah. So that's what I'm saying. I used radius of curvature in my model. I didn't use curvature, which is just one by which is just one by curvature. And I know that curvature and angle are not the same thing, but they are related. So as obviously as my bending angle will increase, my curvature will increase. So even though I'm giving the limit curvature in terms of the angle that the spaghetti is bending when it reaches that, I'm not actually giving the proper like curvature. I
How
think
do you
the
how do you
point is
measure
still.
the angle? How do you measure
Um,
that bending angle?
Uh, yeah, just bending angle. You can see it in like in the tube that I've put. The tube is
Yeah,
of a fixed angle,
I've seen
or
on that protractor you put
yeah, that
spaghetti and you've bent that like one end of the spaghetti, right?
yeah. So
But if you took
I
a longer edge,
right.
right? If you took like a longer edge of the spaghetti, you could have bent it even more. The angle would have been even more then, right?
I
If
no,
you
because
took
I'm holding it down at one point, right? So I don't think I could
You're
have,
holding
because
1 point down, but
yeah,
if you hold the other end of the spaghetti
right.
and say instead of say x centimeters, it's
Yeah.
2x centimeters. You could have bent it further
Um, I I did try
because
with varying lengths of
you
I
can't
no
really
no
find the curvature.
I
You
did
can't
try
really
with
find the
varying lengths
curvature
of
that one side.
spaghetti. No, no, I did try with varying lengths of spaghetti, and regardless of like the overall length, it was consistently breaking at around 25 degrees only. Because the localized curvature, regardless of how big my arms are on either side, the localized curvature remains the same at around 25 degrees. No, so if I say that it breaks at around 25 degrees, it breaks at the curvature that arises when I bend it to 25 degrees. But that's like essentially I'm just saying it in a slightly simpler way, if I'm not wrong.
Yeah, you should just said limiting angle.
Maybe, yeah. Then perhaps
Yeah, you
that would have
should.
been a bit more clear.
Yeah.
Yeah.
Okay,
Also,
with that, we'll conclude.
so
We'll
so I
conclude
have one
stage
more
one.
one more question, sir. I have one more question for Anand.
Okay.
So, if we let's consider braking without the confinement tube, right?
Right.
This is very theoretical in the uh,
Of course, yeah.
spaghetti's nature, right? So, when you broke the spaghetti and you put it under the slow motion camera
Yeah.
and you saw the flexural waves travel, did you notice the nodes and antinodes specifically? Like the waves have antinodes and nodes, right?
Yeah, so they do. I didn't specifically model them because the problem statement clearly says that it's about a
Yeah, yeah,
spaghetti being pushed through a bent tube.
I
So I thought that
understand.
it's just a little out of the scope of the
Yeah,
problem
yeah,
statement.
it
I
is, it
didn't
is.
model
This
it
is
exactly. Yeah.
this is just a theoretical question.
Okay, yeah,
So
fair
I
enough.
wanted to ask, what would you expect the next piece to break at, the next breaking point to be at, if you consider the flexural waves and without the confinement tube, the flexural waves and the antinodes and the nodes of the, you see that the your spaghetti is oscillating.
Yeah.
So you
Yeah.
have obviously your antinodes and nodes there. Which point would you expect the spaghetti to break at?
Um, which point is in like how far along the spaghetti you mean?
Oh,
So
if you
I
have two, like the wave is throughout the spaghetti, right?
Yeah,
If
yeah.
there are
Okay.
two
So
points, the
what point in the
antinode or
wave?
the
Yeah, yeah.
node,
Anti-node.
what point?
Yeah. So I have not looked into the theory enough to be able to answer that because I felt it was slightly out of the scope of purview. Perhaps in later research I could look a little more into
It's
it.
like exactly linked to how the spaghetti
Yeah,
breaks
yeah.
the first time. So you can very easily, I think you should be able to
Okay, yeah.
extend that to this point, right? Because
Uh,
you've established that your spaghetti breaks at a certain limit curvature. Now, if there
Yeah,
is a wave propagating down and there are antinode and node points on the whole spaghetti because of the wave, then there are like all the different points have different curvatures. So
right.
which point could achieve that limit curvature? That's what I'm asking you.
Um, I guess the anti-node because I believe that's where the stress and the strain is maximum. No? But
Yeah.
again, I'm not very sure.